Hello students. Welcome to Varun tutorials. Let's solve question 1. The quantity 1 plus y squared, plus the quantity x minus e raised to the power tangent inverse y, times dy by dx, equals 0. We will rewrite it, identify the standard form, find the integrating factor, and integrate step by step. We start with the given differential equation. The equation is 1 plus y squared, plus the quantity x minus e to the tangent inverse of y, times dy by dx, equals 0. We will label this as line 1. To solve, we divide both sides of line 1 by dy by dx, which is the same as multiplying by dx by dy. This gives our full divided form, 1 plus y squared over dy by dx, plus the quantity x minus e to the tangent inverse of y, times dy by dx, over dy by dx, equals 0. We cancel the dy by dx terms from the second term. Let us write down the simplified expression after this cancellation. This gives 1 plus y squared, times dx by dy, plus the quantity x minus e to the tangent inverse of y, equals 0. Next, we divide both sides by 1 plus y squared to show the division of each term explicitly. This gives line 2, 1 plus y squared times dx by dy divided by 1 plus y squared, plus x over 1 plus y squared, minus e to the tangent inverse of y over 1 plus y squared, equals 0. We cancel 1 plus y squared from the first term. Simplifying line 2 by cancelling terms yields the standard linear form of equation 1. This gives dx by dy, plus 1 over 1 plus y squared times x, equals e to the tangent inverse of y, over 1 plus y squared. Let this be equation 1. This matches the standard form of a linear differential equation in x, namely dx by dy plus p of y times x equals q of y. Comparing coefficients with equation 1, we identify our p and q functions. P of y is 1 over 1 plus y squared, and q of y is e to the tangent inverse of y, over 1 plus y squared. The integrating factor, or IF, is calculated using the formula, e raised to the power of the integral of p of y, dy. Let's recall the related standard integration formula. The integral of 1 over 1 plus y squared, dy, is equal to tangent inverse of y. Let's also recall the related derivative formula for tangent inverse of y. The derivative of tangent inverse of y with respect to y is 1 over 1 plus y squared. Substituting the integral, we calculate the integrating factor. Therefore, the integrating factor is e raised to the power tangent inverse of y. For a linear equation in x, the general solution formula is as follows. X times the integrating factor, equals the integral of q of y times the integrating factor, dy, plus the constant c. Let us substitute our integrating factor and q of y into this formula. This yields x times e to the tangent inverse of y, equals the integral of e to the tangent inverse of y, over 1 plus y squared, times e to the tangent inverse of y, dy, plus c. Combining the exponents in the numerator simplifies the integrand. This gives the integral of e to the power 2 tangent inverse of y, over 1 plus y squared, dy, plus c. To evaluate this integral, we use substitution. Put u equals tangent inverse of y, which gives du equals 1 over 1 plus y squared, dy. Substituting these values transforms the integral into the integral of e to the 2u, du, which integrates to e to the 2u, over 2, plus c. Now we substitute back u equals tangent inverse of y to find our final answer. This gives x times e to the tangent inverse of y, equals 1/2 times e to the 2 tangent inverse of y, plus c. Here is the final required general solution, highlighted and boxed. Let's move to question 2x times the quantity x minus 1, times dy by dx, minus y, equals x squared times the quantity x minus 1 cubed. We will rewrite it in standard form, find the integrating factor using partial fractions, and solve. We start with the given differential equation. The equation is x times the quantity x minus 1, times dy by dx, minus y, equals x squared times the quantity x minus 1 cubed. We will label this equation as line 1. We divide both sides of line 1 by x times x minus 1 to show the division of each term explicitly. This gives line 2x times x minus 1 times dy by dx divided by x times x minus 1, minus y divided by x times x minus 1, equals x squared times x minus 1 cubed divided by x times x minus 1. We cancel x times x minus 1 from the first term, and cancel the common factors on the right. Simplifying line 2 by cancelling common terms in the numerators and denominators gives equation 1. This yields dy by dx, minus 1 over x times x minus 1, times y, equals x times the quantity x minus 1 squared. Let this be equation 1. This matches the standard form of a linear differential equation in y, dy by dx plus p of x times y equals q of x. Comparing coefficients with equation 1, we identify p of x and q of x. P of x is minus 1 over x times the quantity x minus 1, and q of x is x times the quantity x minus 1 squared. The formula for the integrating factor, or IF, is e raised to the power of the integral of p of x, dx. To integrate p of x, we split the fraction using partial fractions. We find that minus 1 over x times x minus 1 decomposes into 1 over x, minus 1 over x minus 1. Let's recall the standard logarithm integration formula, where the integral of 1 over x is natural log of x. Let's also recall the corresponding derivative formula for natural log of x. The derivative of natural log of x is 1 over x. Integrating our partial fractions gives the integral of p of x, dx, equals log of x, minus log of the quantity x minus 1. Using the logarithm subtraction rule, log of a minus log of b is log of the fraction a over b. Applying this rule, the integral simplifies to the natural log of the fraction, x over x minus 1. Now we substitute this integral back into our integrating factor formula. This gives, integrating factor equals e raised to the power log of x over x minus 1, which simplifies directly to x over x minus 1. The general solution for a linear equation in y is given by the standard formula. Y times the integrating factor, equals the integral of q of x times the integrating factor, dx, plus c. Substitute our values of integrating factor and q of x into the formula. This yields, y times the fraction x over x minus 1, equals the integral of x times the quantity x minus 1 squared, times the fraction x over x minus 1, dx, plus c. Simplifying the integrand, we cancel out one factor of x minus 1 from the numerator and denominator. This simplifies the integral to, the integral of x squared times the quantity x minus 1, dx, which equals the integral of x cubed minus x squared, dx, plus c. We integrate the terms x cubed and x squared term by term using the power rule. This yields our general solution, y times the fraction x over x minus 1, equals x to the power 4 over 4, minus x cubed over 3, plus c. Here is the final required solution, highlighted in the box. Let's move to question 3x cubed times sec² times dy by dx, plus 3x squared tangent of y, equals cosine of x. This equation can be reduced to linear form using substitution. We write down the given differential equation. The equation is x cubed times sec² times dy by dx, plus 3x squared tangent of y, equals cosine of x. We label this as line 1. To simplify the equation, we divide both sides of line 1 by x cubed to show the division of each term explicitly. This gives line 2 x cubed sec² dy by dx divided by x cubed, plus 3x squared tangent y divided by x cubed, equals cosine of x divided by x cubed. We cancel x cubed from the first term, and cancel the x squared with the denominator. Simplifying line 2 by cancelling common terms gives equation 1. This gives sec² y times dy by dx, plus 3 over x times tangent of y, equals cosine of x over x cubed. Let this be equation 1. This equation is not linear yet, but we can reduce it to linear form using substitution. Let's put u equals tangent of y. Let's first recall the derivative of tangent y with respect to x using the chain rule. The derivative of tangent of y with respect to x is sec² of y, times dy by dx. Differentiating both sides of our substitution with respect to x gives, sec² y times dy by dx, equals du by dx. We substitute these expressions back into equation 1. This transforms the equation into du by dx, plus 3 over x times u, equals cosine of x over x cubed. Let this be equation 2. This is a standard first-order linear differential equation in u, du by dx plus p of x times u equals q of x. Comparing coefficients with equation 2, we identify p of x and q of x. P of x is 3 over x, and q of x is cosine of x over x cubed. The integrating factor is calculated as e raised to the power of the integral of p of x, dx. This gives e raised to the power of the integral of 3 over x, dx, which simplifies to e to the power 3 log of x. Using logarithm properties, 3 log of x is log of x cubed, and e to the power log of x cubed simplifies directly to x cubed. Therefore, the integrating factor is x cubed. The general solution formula for our linear equation in u is u times the integrating factor, equals the integral of q of x times the integrating factor, dx, plus c. We substitute our values of integrating factor and q of x into the formula. This yields u times x cubed, equals the integral of cosine of x over x cubed, times x cubed, dx, plus c. Cancelling out the x cubed terms from the numerator and denominator simplifies the integrand. This simplifies to u times x cubed, equals the integral of cosine of x, dx, plus c. Recall the standard integration formula, the integral of cosine of x is sine of x. This integration gives u times x cubed, equals sine of x plus c. Finally, we substitute back u equals tangent of y to get the required general solution. This yields x cubed times tangent of y, equals sine of x plus c, shown here in the final box. Let's move to question 4, cosine squared x, times dy by dx, plus y, equals tangent of x. We will divide by cosine squared, find the integrating factor, and integrate using substitution and integration by parts. We write down the given differential equation. The given equation is cosine squared x times dy by dx plus y equals tangent of x. We label this equation as line 1. We divide both sides of line 1 by cosine squared x to show the division of each term explicitly. This gives line 2, cosine squared x times dy by dx divided by cosine squared x, plus y divided by cosine squared x, equals tangent of x divided by cosine squared x. We cancel cosine squared x from the first term. Simplifying line 2 by using the trigonometric identity where 1 over cosine squared is secant squared gives equation 1. This gives dy by dx, plus secant squared of x times y, equals tangent of x times secant squared of x. Let this be equation 1. This is a standard first-order linear differential equation in y, dy by dx plus p of x times y equals q of x. Comparing coefficients with equation 1, we identify p of x and q of x. P of x is secant squared of x, and q of x is tangent of x times secant squared of x. The integrating factor is calculated as e raised to the power of the integral of p of x, dx. Substituting p of x gives e raised to the power of the integral of secant squared of x, dx. Let's recall the standard integration formula where the integral of secant squared of x is tangent of x. Let's also recall the related derivative formula for tangent of x. The derivative of tangent of x is secant squared of x. Evaluating the integral gives the integrating factor as e raised to the power tangent of x. The general solution formula for a linear equation in y is y times the integrating factor equals the integral of q of x times the integrating factor, dx, plus c. We substitute our values of integrating factor and q of x into the formula. This yields y times e to the tangent of x equals the integral of tangent of x times secant squared of x times e to the tangent of x, dx, plus c. Let us evaluate this integral using substitution. Put tangent of x equals t, differentiating both sides gives secant squared of x, dx, equals dt. Substituting these terms simplifies the integral to the integral of t times e to the t, dt. To integrate this product of functions, we recall the integration by parts rule. Applying the rule, the integral of t times e to the t, dt, is equal to t times e to the t, minus the integral of e to the t, dt. This simplifies to e to the t, times the quantity t minus 1. We substitute back t equals tangent of x into our equation. This gives y times e to the tangent of x equals e to the tangent of x times the quantity tangent of x minus 1 plus c. To solve for y, we divide both sides of the equation by e to the tangent of x. This yields our required general solution, y equals tangent of x minus 1 plus c times e to the minus tangent of x. Here is the final general solution highlighted in the box. Let's solve question 5, dx plus x dy equals e to the minus y times secant squared y, dy. We will rewrite it with respect to y, find the integrating factor, and integrate. We start with the given differential equation. The equation is dx plus x dy equals e to the minus y times secant squared of y, dy. We label this equation as line 1. To find the standard form, we divide both sides of line 1 by the differential dy to show the division of each term explicitly. This gives line 2, dx divided by dy, plus x times dy divided by dy, equals e to the minus y times secant squared of y times dy divided by dy. We cancel the dy terms from the second and third terms. Simplifying line 2 by cancelling the dy terms in the numerators and denominators gives the standard form. This gives dx by dy plus x equals e to the minus y times secant squared of y. This is a standard first-order linear differential equation in x, dx by dy plus p of y times x equals q of y. By comparing coefficients, we identify p of y and q of y. Here, p of y is 1, and q of y is e to the minus y times secant squared of y. The integrating factor, or if, is calculated using the formula, e raised to the power of the integral of p of y, dy. Let's recall the basic related integration formula. The integral of 1 dy with respect to y is simply y. Substituting p of y equals 1 gives e raised to the power of the integral of 1 dy, which evaluates directly to e to the y. The general solution formula for a linear equation in x is as follows. X times the integrating factor equals the integral of q of y times the integrating factor, dy, plus c. We substitute our values of integrating factor and q of y into this formula. This gives x times e to the y, equals the integral of e to the minus y times secant squared of y, times e to the y, dy, plus c. Using exponent rules, e to the minus y times e to the y simplifies to e to the 0, which is 1. This simplifies the integrand directly to the integral of secant squared of y, dy, plus c. Let's recall the related standard integration formula where the integral of secant squared of y is tangent of y. Evaluating the integral yields our required general solution x times e to the y, equals tangent of y plus c. Here is the final answer highlighted in the box. Thank you for watching. If you found this helpful, please like, share, and subscribe to Varun tutorials. Turn on notifications so you never miss a new video.